Dr. Pradeep is the Deepak Parekh Institute Chair Professor and is also a Professor of Chemistry at the Indian Institute of Technology, Madras. He received both BSc and MSc degrees from the University of Calicut and PhD from the Indian Institute of Science, Bangalore. He did his postdoctoral work at UC Berkeley, California, USA. His research interests are in molecular and nanoscale materials. In addition to authoring several books, he has authored or co-authored an impressive 525 scientific papers in international peer-reviewed journals and has over 100 patents. Wow. Or patent applications to his credit. He has involved in the development of affordable technologies for drinking water purification, and some of them have been commercialized. His pesticide removal technology has reached about 10 million people. Along with his associates, he has incubated 7 companies and 3 of them have production units. His arsenic removal technology, approved for national implementation, is delivering arsenic-free water to over 1.3 million people every day. He has received several awards, including the Bhatnagar Award, Birla Science Prize, National Award for Nanoscience and Nanotechnology, India Nanotech Innovation Award, J.C. Bose National Fellowship, and National Water Award, the World Academy of Science Prize in Chemistry, Nikkei Asia Prize, Prince Sultan bin Abdulaziz International Prize for Water, and most recently, the Win Future Prize. The nation conferred Padma Shri on him in 2020. He is a fellow of all sciences and engineering academies in India, the World Academy of Sciences, and American Association for the Advancement of Science. He has also received the Lifetime Achievement Research Award of IIT Madras and Distinguished Alumnus Award of the Indian Institute of Science. As a part of philanthropy, he supports a school in his village where 500 students are on rows. Please join me welcoming Dr. Pradeep, and I request to him to deliver his lecture, Atomically Precise Clusters for Applications.
Good. Thank you. It's always a pleasure. Can we switch off some of these lights? Is really required, some of these top lights? No. It's always a pleasure to come back to my dear college. And this is, today is our 33rd wedding anniversary. Actually, on that day, I came here because Farook College is dear to me. It's a homecoming always. Professor Chandrasekharan talked about transformative subject. This transformative subject has to be the need to make it circular as well, in every respect. And I am going to tell you about what is actually happening to this transformative subject in the molecular regime of matter at the nanoscale, where matter is becoming atomically precise. And I'm going to take a few examples of such atomically precise matter, how this matter is going to contribute to sustainability, as Professor Chandrasekharan talked about. I will not have time to tell you everything about, or most of it in this subject area. I'll take a few examples and illustrate this. Now, the moment one talks about atomically precise matter, and you might be thinking that this matter is essentially matter in the laboratory, on your workbench. It doesn't translate to society. And I will show you that it is indeed possible to take such atomically precise materials to applications. And in that process, you will also see that it is not going to be chemistry, It is going to be chemical engineering, it is going to be mechanical engineering, it's going to be electrical engineering, electronics, computer science. It is now going to be a frontiers. It's going to be frontiers of chemistry where every subject is essentially intermingled. The boundaries disappear. So all of these will have value for you. When I was a student here at this college, I did not know, I was not exposed to the frontiers. When I went to do a PhD and then started doing science of my own, I realized that these boundaries collapse and they essentially disappear. So I would like all of you to explore those boundaries using some of these examples. Of course, more examples will come in the course of this series. I was planning to tell you about new boundaries of materials. One such boundary, evolving frontier, is atomically precise clusters. I started out working in this area with one person who is sitting here in the audience. His name is Shibu. He is now teaching at your university, Calicut University. So the very first paper, of course, there was a paper before his time, but then the activity started, intense activity was started in the group with Shibu. So what you see is a particle. It's a particle of gold. Now, each one of these is a gold atom. There are 25 of these gold atoms. And years ago, when you were to tell people a 25 atom particle exists in a bottle, people wouldn't believe it. Today we make this molecule in the laboratory. It is not that we make one molecule, there are many molecules that we make. I said molecule. 25 atoms, or a piece of 25 atoms of gold, some years ago, people would have called a cluster. Today, I call this as a molecule because we have all molecular properties. And you'll soon see that. This has a molecular weight. This has a solubility. This has a crystal structure. This has its associated thermodynamic properties. It has its optical absorption spectrum. It has its electronic structure. It has a condensed, in the condensed phase. It has its associated band structure. So all of those. So great. Now this is not just this molecule. There are many such molecules, and there are several examples I have written here. There are today over 500 such molecules. This is another example. There is a 25 atom silver, 44 atom silver particle, and these are silver atoms. The green ones are silver atoms, as well as this orange one are silver atoms. There are sulfur atoms, there are carbons, etc. So I go back and tell you, sorry, I should go back. It's only going in one direction, is it? Okay. So this is, I said 25 atom gold. It is not that it is only 25 atom gold. It has certain protecting ligands around, and these are the ligands. So this is sulfur, and in this particular case, there is a CH2, some phenyl group, or there may be directly a phenyl group and some CH3 that is connected. So essentially this is, or it may be one phenyl group and there may be two CH3 groups. There are several such ligands that are present. Now these kinds of materials, that subject area is expanding. So there is another speaker in this audience. Her name is Ananya Bakshi. She studies the mass of these cluster systems. So today, we can measure mass spectrum of such particles to very high masses. In fact, there are friends of mine who put viruses in mass spectrometers and measure mass spectra of viruses. So this subject area is very big, where you can expand, well, this mass range is only now 660,000. It can be 600,000 or 6 million. This entire mass range is today studied, and we make larger and larger particles. Now, these particles can be atomically precise, meaning when you have 1,000 atom particles, you can have 1,000 atom particle or 1,001 atoms in this particle. So 1,000 atom particle and 1,001 atom particle. And you can have 999 atom particle as well. And now it is not that there is specificity in the number of atoms, there's also specificity in the structures. Now, that structure can be studied as well. In the lab, we make another particle here. You see 144 gold atom particle. You see a mass spectrum of that. These are two different mass peaks of the same material. One is a 3+ charge state, another is 2+ charge state. This is essentially to tell you that we can make all these. When you make all that, you can crystallize these. When you crystallize it, you can get crystal structures of this. This subject is expanding also because we have great computational insights into materials. So when you have structures of this kind, you can put these molecules into a computer and ask this question, what are the energy levels of this? So from such studies, we know that these kinds of materials are stable because of an unusual electronic structure. And they are also stable because of some unusual geometric structures. So there are geometric and electronic reasons why they are stable. I'm not getting more into these details. When we have such materials or molecules, we can assemble this, as I told you, create structures. Now, you create a structure, let us say a piece of matter, a macroscopic object. This macroscopic object is also atomically precise. Now, you might wonder, well, sugar, a piece of sugar is atomically precise. But then, in that sugar or crystal of sugar, there can be varying number of atoms, varying number of molecules of this sugar, glucose or sucrose or what have you. But then in these materials, you can create a small piece of gold or a silver or a platinum or nickel or palladium with precise number of clusters having unique properties. If you change that number or species, the properties will change. That is a unique family of materials today. I told you that they have properties. So if you take a molecule such as water, you have a lot of properties. In fact, the properties of water will run into several pages. And I have written only a few properties here. Molecular weight, crystal structure, critical pressure, critical density, etc. But today in these some of these atomically precise clusters, we have a molecular formula. We have a weight, we have a structure, we have an absorption, we have reactions, we have assembly, we have co-crystals, we have ionization potential, electron affinity, and all that. But we still don't know a whole lot more about these. There are a lot of opportunities in understanding, for example, phases, the phase transitions, the critical pressures, the mechanical properties, the electrochemical properties, and all that. So we have written a book in this area. Several of the people here have contributed as well, my former colleagues as well. Now, if you wish to know, you should look at this. This is a 2023 book. So when you say that these are molecules, one question that comes to everyone is that these molecules, are they reactive just like molecules that you have or you have studied? So we were asking this question. What you're seeing is a picture of a cluster, which is in visible light, it is colored. In ultraviolet light, it is luminescent, red luminescent. So these molecules are moving around in this solution. So one day I was thinking that, will they be having chemical reactivity just like normal molecules? So we wrote a paper on that by studying this reactivity with mass spectrometry, advanced mass spectrometers. What is shown in this paper is that if you take a molecule of this and another molecule, this one, you can have chemical reactions between them in solution just like A plus B leading to C plus D. This is to say that you have a stoichiometric reaction, you have a thermodynamics associated with it, you have a kinetics for it, and you have mechanisms for it. Now you say that if all these happen, these are really molecules. Well, we studied this in detail. So if you take two molecules like these, and these are some acronyms to say that this is one particular ligand, fluorothiophene, I say, and this is also fluorothiophene. In order to avoid complications in chemical reactions, we have deliberately chosen these ligands to be the same. Now you put this in solution, you are mixing this, and you are measuring a mass spectrum of this. To begin with, we measure the mass spectrum of this, and in that there will be a peak due to this, 0, and there is another peak. This peak is due to a fragment. So if you look at this, this is AU25 FTP18, and this is AU21 FTP14, corresponding to a fragment, a loss of a fragment. You mix these two, suddenly you see a peak here. Suddenly you see many peaks here. These peaks are essentially one atom of Ag has gone into this and one Au has gone into this. That peak comes somewhere else. I am not going to show you that. But it is essentially to say that there is some exchange chemistry that is happening in this. Series of exchanges happen in this fragment as well. Wait a little while. After 2 minutes, you go to, let us say, 10 minutes, you get more exchanges. And a little later on, this peak will disappear completely, which I am not showing you. Later on, only one peak or a few peaks will come up in this reaction. Now you ask this question, how does it happen? You go to a computer. Can we have enthalpic reasons? Can we have entropic reasons? Can we have free energies associated with this? Can we have specific structures associated with it? One atom from Ag44 goes to Au25. You ask, which atom goes? Which atom will substitute? And in the course of evolution, how many different structures form? All of these we study. But you know, this is even more surprising, that if you have one molecule like this in solution, and this interacts with another molecule in solution, and atom is exchanging. I was asking one day this question that this is moving around. Let us say this cluster is in the pure form. Let us say there is another cluster this cluster is encountering another cluster. Will it be possible that one atom from this cluster will exchange with another atom in another cluster? So this is like isotopic exchange. We know that this happens in water. H2O meeting another H2O, hydrogens will exchange. And this we know it very well by studying H2O and D2O mixture. If you take H2O, D2O, you mix it together, you get HDO. You don't get H2O. You don't get D2O. This is because of a rapid atom exchange that happens. Now you wonder, is this possible in an atomically precise cluster? Then you know that molecular science of the kind that we are used to happen in such materials as well. So we made this cluster, Ag25 with one isotope, 107 isotope. This is like H2O. But silver has another isotope, 109. We made another cluster, 10925. So this is like D2O. And you know, this is pure. And this is pure. So therefore, it will have an isotopic distribution corresponding to pure Ag25 with 107 isotope. Now you might be wondering why there are many peaks. Mass spec peaks. It is because even when we have 107 isotope, which is pure, you have sulfur atoms here, they have 4 isotopes. There is a 32 sulfur that you are familiar sulfur. So there is 33, 34 and 36. These isotopes exist. And carbon has 2 isotopes. 12 and 13. Hydrogen has 2 isotopes. So all of these put together is an isotopic distribution, and there is a peak corresponding to 5142 is the maximum. Now there are, in this particular case it is 109, so the peak is 5192. So this is 50 mass units more. That is what you have, it's a pure compound now. You mix these two together, H2O and D2O. Boom, you get this peak disappear completely, this peak disappears completely, and what you get is a completely different distribution corresponding to 50-50 atom distribution, isotopic ratio of 50-50 of 107 and 109. So what I wanted to tell you is that molecular science happens in atomically precise pieces of nanoparticles. And we understand this in great detail today with even more experiments. But what I just told you, if you extend that science further, this need not stop. This kind of exchange and chemistry need not stop with that 25 atoms or 44 atoms. It can go to 1,000 atoms, 3,000 atoms. So here is that example wherein particles of various sizes are there, and these are called nanoparticles. You might have been told about this. This, if you add some clusters to it, they react, and there is a lot of exchange. And what you get are highly uniform particles at the end. This is to say that molecular science extends far beyond the normal molecular regime. The mass of these will be like 300, 400,000 Daltons. Today we are studying this at a 1 million Dalton level in the laboratory. I am not having data to show you that. So when I say that all these are now forming uniform particles, you can use the science to grow crystals of these particles which are highly uniform, and we see these crystals. Oh, molecular science of the kind that we just now talked about can be expanded to larger and larger sizes. Today, we also study these particles. They can not only react, they can also form supramolecular assemblies. So here is a nanorod, a rod-like particle made of gold, having several thousands of atoms, 10,000 to 50,000 atoms. And they are in this form. They have ligands on these or surfactants on the surface of it. You can have hydrogen bonding between a cluster and these ligands on the surface of these rods and create structures, and you can observe these structures in the TEM. So these are the, to begin with, these are the rods, and finally you assemble these clusters on these rods and you see these unusual structures coming up. We create composite structures. So why are we doing all this? We do all that to understand the new or sort of discover new properties. One such property we look at in great detail is their chemistry with molecules and ions in the context of clean water. So we study these chemical reactions, chemical interactions with nanoparticles, study their basic science, that is this number one, and we understand specific aspects such as this catalysis or disinfection and water harvesting and different kinds of areas, and we convert the science that we discover to products. What Professor Chandrasekharan talked about, we get into clean water through these products, which I am, in a previous lecture, I talked about in this seminar series, what kind of science we do. But where is this cluster getting in? Those are really not applications of clusters. One way clusters can get in is to create new sensors. So in fact, if you have a water purification plant which is supplying clean water to all these homes, we need sensors to measure whether water is clean, how much of water is going into each one of these homes. So for that, we develop new sensors. These sensors have to be connected to mobile phones, and we create data. In the country, we are developing these, and we are monitoring this water quality across the country from Srinagar to Kanyakumari. I don't do all these on my own, but several of our people do that. So I show you a video that we do in this context. I hope I can play this. What you see is in a region called Punjab, where there is arsenic in drinking water, and we develop technologies to remove arsenic from drinking water down to 2 parts per billion. It is far below the drinking water limits, from far above drinking water limits, using advanced materials like using these plants. These plants use materials, nanoscale materials, and we use monitoring devices to measure water quality and quantity. Now, these are today IoT controlled, Internet of Things controlled. So you control the water quality and quantity. In addition, we measure various parameters of the plant, such as the amount of electricity used, amount of what is the voltage that is coming in, what is the pump's health, etc. So I'm moving this. This is not the objective. Now, if you want to study this, arsenic in drinking water, one way to measure this very well is by doing something called biosensors. And you know, there are these molecules called arsenite oxidase. It's a protein. This converts arsenite to arsenate, just as what the name implies. But in that process, 2 electrons come out, and this you can measure just like a blood glucose monitor, which is an electrochemical device similar to this. In this particular thing, what you have is this particular arsenite oxidase enzyme. It is sensitive only to arsenite, just as all biosensors are. what you have in the sugar, the sensor that you have. It is sensitive only to that and no other biomolecule in the blood, and that is why you can measure it accurately. There are a lot of other developments that people have made, how to do better electron transfer using carbon nanostructures so you can measure this arsenide in water. But nobody has ever measured arsenic in drinking water down to 10 parts per billion. That is the limit of arsenic in drinking water. So if you have a device to measure arsenic in drinking water down to 10 parts per billion, the device that I showed you can do wonders in eliminating arsenic in the world. So any student who goes, or anyone who goes to field, let us say you have a device and put that in water and you see there is arsenic in water, you have a technology to solve it, the world will be arsenic free. Today we don't have this device to measure arsenic in the field. So as a result, you have to take this water, go to a laboratory 200 kilometers away, test it with advanced measurements which require several crores of infrastructure and trained manpower to do. You can't do that in the field. How about an advanced arsenic sensor using nanoclusters? This is not the first time that we got this kind of a thought. We have developed several materials. So these are membranes in which clusters have been put in, and I told you, if you remember a picture, in ultraviolet light, some of them are brightly luminescent. Obviously, these membranes also are luminescent. The luminescence can be made as a sensing methodology, and it detects arsenic or other metal ions in water. Here I am showing you electrospun fibers. Using this, you create a membrane. The fibers are coated with two different materials. One is green emitting, another is red emitting. Now, both are together, but in green intensity is far more, so you see only green light ultimately. But when these red fellows, or the molecules responsible for red, which are clusters, are sensitive to given analyte, this intensity will go down, only green intensity will come up. That way, you can detect the presence of tiny, tiny concentrations of ions. So here, the luminescence of that cluster disappears because of one contaminant, mercury. Just 9 ions of mercury can do this wonder. So we showed that using nanostructures, original nanostructures containing 2 emitting species, red and green, but as I told you, it shows only red because red intensity is far more. You expose it to mercury containing species, this mercury fellow intensity disappears, or the red intensity disappears due to mercury, green comes up, and you can detect a few ions in drinking water. But all these are great. But you know what happens is that these cannot be put in the field because these clusters are not stable. I told you fantastic science with this. I can make these clusters, put it in the laboratory, very stable, at 4 degrees centigrade, you see? At 10 degrees centigrade, at 25 degrees centigrade, but in the field it is 45 degrees centigrade. And it has to work in the field. So you need thermally stable clusters. We have achieved that now. Here is a cluster, 21 atom cluster, and this guy has a, well, you see a mass spectrum. You have an optical absorption spectrum. It is great. It's a great, good solution. It can be made into crystals, and we have crystals of these. You have a crystal structure, beautiful structure. So this is a carborane thiol protected cluster, and what you see are carboranes. And this is the inner cluster core that you have beautiful crystals that you have. Lots of these crystals we make every day. And you know what? These are thermally stable. You see the thermogram is 338.9 degrees is when you have a mass loss. Stable up to 200, 250 degrees centigrade. In solution, it is stable up to 100 degrees. Beautiful. And what can we do with now these materials? Well, we can create sensors. Here is another cluster in the group. It is cobalt 6S8, and this is beautiful crystals of this, and this is crystal packing, and this girl from Calicut, she did a fantastic job in the group. She used Electrospray as a method. This uses a 5,000 rupees high voltage source and a solution of this cluster, which you can make in an undergraduate lab. Of course, you need chemicals. You put that in the solution, and there is an electrode here, a wire, and then apply this potential and you get a spray, and the spray she makes, in the spray you have droplets of this solvent, electrospraying it. It contains these clusters and depositing these solvents on the surface of water. Fine water, right? Fine surface. And you see that spray, you can't see with your eye, and you shine a laser and you see this scattering from such clouds, you know, scattering occurs, and this is that scattering of the green light that you see. So you have a spray that is coming. It's depositing on this water surface, and when we took that film out, you see that this kind of unusual structures form, and in the greater expansion, you see they are like these nanostructures. And these things are very highly sensitive to arsenic. And what? In clean water with no reagent added, you get sensitivity, you see arsenic cyclic voltammogram up to 5 ppb. 2 ppb, 1 ppb, you can measure a cyclic voltammogram and you see that. It's extremely sensitive. So what is it good for? Can develop a sensor with it. Why is it sensitive? Because of certain kind of bonding that arsenite does to that cluster system, which you can compute using computational methods. I'm not getting into that detail here. So you are sensitive. So why is it sensitive? It is because of that cobalt's unusual chemistry. With this cobalt's unusual chemistry, people have studied before, cobalt oxide, cobalt sulfide, all of them. But you see, using cobalt nanoparticles or cobalt oxide nanoparticles, you can sense arsenic to about 750 ppb. So that is 10 millimoles of micromoles of arsenic, 10 ppb. That's the first data point. And this is not useful because the limit is 10 ppb. But this kind of a thing is possible with cobalt, but we could achieve far, far lower detection limits. And so what are we doing? We make a small potentiostat, which can be put in the pocket, and put this electrode, which you can buy, you have it in the sugar meter, you have such electrodes. But it is composed of these guys. The data will come on this mobile, and the data will go on to the cloud. And using cloud-based algorithms, you can measure the quality of water. And it does exactly this arsenite to arsenate, similar to arsenite oxidase enzyme. And I'm going to show you many other efforts we did in the lab. There's no point in talking about all that. 5 years of effort to make advanced materials like graphene or graphenic materials to get sensors, but we could achieve sensing only down to 10 parts per billion here or 15 parts per billion. By that time, the signal is so weak. We wrote papers, of course, but it is very difficult to put this in the field. That again, we calculated, etc. I'm going to show you what this is going to do. See, this is a tiny machine that you can put it into your pocket, And you can do electrochemistry, and I'm going to press this button now, and no, sorry, I have to go back, and here I'm going to show you a video. Is it playing video? I'm sorry, it may not be playing, or what? I cannot show you that thing. It's essentially to tell you that that little device in the pocket, you put this electrode, not exactly that electrode. It is actually playing. But I need to go back to anyway. Yeah, so this device that I just told you, if you look at it from a, so the data are being collected using some electrode. If you look at it from that distance, I don't know whether you can see, you see a line that is going, that is the cyclic voltammogram that is running, and you are going to see a peak. This data are coming on this internet, and you can measure this water quality, and that device costs 7,500 rupees. If you make it in quantities, maybe 5,000 rupees. So what does it mean? Of course, we can measure many other ions, but arsenic is very important for the country. So this data, this is already now several months old, so therefore our software and all that have improved substantially. I'm going to move this further, hopefully it will move. So what does it mean? It means that we can measure arsenic quality not only for India. Now this device can go anywhere because the data can come through the internet. So these are all the places where arsenic is available, or arsenic is in water. Arsenic is available everywhere. Arsenic is in drinking water beyond the concentration. This is in these places. So you can measure quality of arsenic across, and one can probably solve that problem. And that was what I wanted to tell you. So it is possible today to address solutions or create solutions of this kind using advanced materials. Arsenic is only one of them. There are many, many things that you can do, many things that you can do for your health, many things that you can do in the context of diseases, energy, sustainability in multiple dimensions. We have a large team of international and national collaborators. Several pictures I have put, several others I have not put pictures. They're all world leaders in respective areas. This science that I did was done, or some of the students engaged in research are shown here. This is a girl who did that work that I showed you. Her name is Anagha Jose, and this is science was supported by the Department of Science and Technology. Thank you very much. I have kept 8 minutes for questions.
A few questions.
Yeah, thank you.
So, Dr. Pradeep, I don't know how relevant my question be. Anyhow, you told just now, depending on the size of the clusters, the nature and the properties of the clusters also changes. Now, I'm just thinking about the homeopathic medicines that is made, the arsenic oxide that is dissolved in alcohol. From that, they take one part of it and dilute it with water. Again dilute, then make it potency. So, depending upon the potency of this, they say the effect also changes. is there any relevance whether there may be nanoparticles that is going into, because the homeopathic medicine is based on this. Just now when you talked about, I was thinking about that one. So you can have an answer this.
Homeopathic medicine and the nanomaterials relevance in this context, this is being studied by a few people in the country. So this is in IIT Bombay. There are colleagues of ours who do this activity. Summary of this science is that, well, what they say, this is not my activity, is that there is no material at that dilution. There is nothing that is going to be there at that dilution. However, there can be reasons why materials can be there, because at that level of dilution, many things are sticking on the surface, the glassware, on the surface of this liquid, because there are so many ways by which particles can be present. But if you go on calculating what happens at that dilution, chemical principles will tell you that there is no molecule there. But still one says that there are effects. Now they say that these effects could be associated with surface-bound particles in such systems. This is one theory, and people have not been in a position to see particles at that dilution using the techniques of science. They have left that. But there are also others, equally, one would say, emphatic about the relevance of such science, and they still argue that debate is not settled completely. This is my current understanding of it. Professor Chandrasekharan, you have something more? That's what I know.
But sir, the molecules will never disappear, I think. The molecules will be still there because they are not removing it.
Yeah, sure.
Even if one drop is there, according to Avogadro's, we say that there will be molecules, sure. So we cannot detect it, is it not?
Correct. That's what I'm trying to say. In solution, they don't detect it by methods. So if you take 2 molecules in, let us say, 1 liter, or 200 molecules in 1 liter, keep on diluting, a limit will come, you can't see particles in 1 ml. So you get to that limit, and this is the limit wherein things start having effect. Where is this effect coming from? Apparently the effect has to be from somewhere else. This is the surface-bound species coming. Thank you.
Thank you.
More questions? Here.
Yeah, there is something here. Yes, atoms are exchanging.
Clusters. Probably that reaction, clusters would have collide each other.
Yeah.
What prevent the clusters aggregate at that time?
Good, very good. So clusters do come and form aggregates. In fact, when an atom exchanges from one cluster to the other cluster, there is an in-between state wherein 2 clusters come together. We detect this. We study the mass spectrum of that. And what happens subsequently? So they do this forms of interaction, and then they move away. Just like water, they come together, there is this hydrogen bonding that occurs, molecules move away. This happens in solution. In the case of clusters, their interactions are sufficiently strong so you can detect this in the gas phase by mass spectrometry. In solution too, probably in different kinds of nanosystems, such interactions occur. We know that protein aggregates are there, you can detect them. Similarly, these aggregates also occur. The science of exchange happens through a transition state of aggregates.
Thank you, sir, for the wonderful talk and the work, of course. So I have a couple of questions. So have you looked at the role of the ligand for this reaction of those clusters. Suppose like I'm thinking if you have some attractive interaction, even so in that matter, let's say proteins, antigen antibody if you put.
Yeah.
So will it be facile or what would be the effect of that?
So there are some, let me put this in long years of research into a few sentences. So there are reagent or surfactants or ligands wherein reactions can be stopped, completely eliminated. Or there are facile ligands where such things are far more feasible. There are cases wherein some ligand exchange occurs and that's the end of it. There is no metal exchange that occurs. Now I can take this further to say that specific structures do get formed. Sometimes one particular site of that cluster alone, you can do substitutions and chemistry driven by thermodynamic structural reasons.
So is it also possible to make it reversible once this reaction happens between the metals? Is it possible to make it reversible to the segregated?
These cases that I just told you, they're all largely, the free energies are way rock bottom. Getting them back is really going to be, free energy-wise, is difficult. One of the major reasons in these nanosystems when such a chemistry occurs is entropy. Atoms are everywhere. Now collecting them back and creating a reordered structure is going to be entropy reversal. This is extremely, it is not that it is impossible, but again another process has to be done to collect these atoms back. Nobody has seen such reversal.
One last question.
Yeah.
So for the arsenic detection,
Yeah.
is it, will it be good if you have something like colorimetric sensor? Like, so, just using the color you can basically detect?
Absolutely. This is what people are after. But there is no colorimetric sensor at that concentration. Remember that this real water is not what you have in the laboratory with some arsenite or arsenate added. Real water is something with 100 things. You need to get this alone. And most of the time, real water is dirty. So you need to measure with that water without any purification, without any chromatographic methods, without any pre-concentration, direct measurements. This is where solution phase chemistry has not been successful so far, and no kinds of colorimetry or fluorescence and all. There are papers that you will see, but none of them can be applied.
Thank you.
We can still publish a lot of papers with fluorescence and all that.
Sure, thank you.
Yeah.
Maybe
There are a
few questions.
Hi, sir. It was a nice session. You were showing some beautiful crystal structures. So my question is that what was the method of synthesis of that particular crystal structure? Mainly, we need to study the structure, electronic, and the other properties by considering the crystal structure. So when I was in my project work, I tried the vapor diffusion method and the layer method and some slow evaporation techniques, but I couldn't get a crystal. So it was my dream to get a beautiful crystal, but I couldn't do that. What was the method?
All that you said are the same methods that we have used, but then we did this again and again and again and again.
Yeah, I have only 1 month period for the
Yeah,
master's
so-
work, so I couldn't find out that thing.
So people, now that you asked this question, please give me 1 minute to answer this particular thing. Somebody went to Oxford. Oxford is full, beautiful lawns. And somebody was watering the lawn, right? Gardener was watering the lawns. And an American went there and asked this gardener, how do you make these beautiful lawns? And the gardener, very simple looking gardener, apparently told this American professor that it's very simple. All that you do is you come in the morning, water the plants, do it every day, do this year after year. For 900 years, you get a beautiful lawn. So you do this many, many times, and you realize where exactly the problems are. You solve that. These methods are just like vapor diffusion or coarse layering and such methods. Nothing so unusual. Those people who do crystallography, proteins, they know that they do this crystallization for 6 years, 10 years. So some of them, we are in a position to crystallize. 200 or so clusters have been crystallized so far. I'm sure that this will be possible. We also struggle through this. Many crystals that we haven't produced crystals for many clusters.
Thank you, sir.
Thank you.
One more question.
There was a girl who wanted to hear. Yeah, go ahead. Yes, Jairam.
There is one question about the surface functionalization.
Yes.
There is a metallic cluster and another metallic cluster. If you are linking together, like, is there any changes will occur in physically or maybe electronically or something?
Beautiful subject. That is what conductivity, and many people do predict that these systems can also probably show superconductivity.
Okay. Is there any covalent bonding between, like, suppose there is a carbohydrate, one metallic cluster and then amine functionality? All this work is there in this metallic cluster field?
There is significant covalency in this bonding. There are, of course, depending upon the type of ligand, you can vary this across. The extent of covalency can be modified. We do create such structures as well. Thank you.
And then last question, like, see, it's always a bulk scale synthesis.
Yes.
Like, how much we can do in this metallic cluster field?
You can do a whole lot. I think the entire periodic table on the right side, in the transition metals, a few have been already attempted.
Yeah.
Lot more to be done. Lot more can be done on alloys, multi-metallic alloys. We know only about bimetallic and trimetallic systems. Lot more is possible. People think in terms of high entropy alloy clusters. 5 elements or more. Like organic chemists do, 13, 14 elements in one molecule. That's the limit. Can we create such structures and induce probably all kinds of properties into a cluster system? Lot of different kinds of catalysis is known today. Professor Chandrasekharan was talking about ammonia synthesis in the context. I was telling you that this last week, somebody has made ammonia synthesis possible with silver clusters at room temperature. But to what extent and all that, this may be a few molecules or something, but we want millions of tons. That's another story. But this is how science is expanding in that.
Thank you so much.
Maybe time for one last question.
Yeah.
Sir, I actually have like 2 more questions.
Oh, if the chair allows. Otherwise we can talk outside. Yeah.
Okay. So one of my question is regarding the clusters that you have formed using like silver and gold, like atomic precise one. And like silver and gold both have like different weights and different volumes, right? So if you're incorporating
silver and gold are nearly the same, 2.88 angstrom and silver, and 2.88 in gold, 2.885 in the case of silver.
Okay, so that is the reason why like you could easily incorporate both into one nanocluster.
There is no difficulty as far as size-wise, yeah.
Okay. So my second question is whether the sensor that you have prepared is specific only towards arsenic, or is it for cadmium and bismuth?
This particular one is arsenic. We have other number of clusters. You can make this very useful for other metals as well. So that is how you do. If you want to sell something, you want to have one precise thing. The glucose meter, you cannot measure alcohol in that, right? Do you?
No,
you can't
sir.
measure, right? That's what it is.
Okay, so that's all. Thank you.
Thank you, Pradeep sir. Please join me thanking Dr. Pradeep once again.
Thank you.
And let me hand over a token of love to Pradeep sir.
So thank you very much. Thank you very much.